Hi, Pratibha. Pratibha, are you there?
Yes, sir. She's a little less audible.
Oh, okay, okay. No, I just want to make sure Professor Gaurav, who will be joining, so he will be the actual person who presents. So I'm assuming he will be able to share screen. Just want to double check.
Yeah, yes, sir. Even he will be able to share the screen.
Sure, yeah, okay. Yeah, thanks.
Sushmita and Pratibha, everything under control?
Hi, Raj. Yes. Yeah.
Okay, cool, cool, cool.
Yeah.
Best of luck.
Yes. I'm audible, right?
Yes, yes.
Yeah.
My volume was low. I was just trying to adjust that. Now it's I can hear.
Yeah. 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 Yes.
Yeah, good afternoon. Pratibha, I'm just waiting for Professor Gaurav to join. So we'll start once he joins. I think he's probably connecting now.
I'm trying to call Professor Gaurav, but I don't have his
Hello, sir. Hello, sir. Am I audible?
Hey, yeah,
Yeah.
you're audible. Yeah.
We are reaching Gaurav, sir. I think
Yeah,
he'd
I
be.
told him, I called him. I just sent
Yeah.
him the link, so he should
Yes,
be
sir.
fine.
Yes, sir. Yes, sir.
Yeah, so for those who are all joining just now, we're just waiting for Professor Gaurav to log in. Um, Maybe some login issues he's having. Just 1 minute. Yeah, Susmita, if you can unshare your screen, I think Professor Gaurav just joined, so he can share his screen.
Yes, sir. Yes, sir. Yes, sir.
Thank you.
Yeah, a small comment. We're starting late, but we'll still have to end the session on time because there are other tutorials after this. People might want to
Sure.
join
Yeah,
those.
yeah. We will end on time. Yeah.
Okay, thanks.
Thanks. Yeah. Yeah, Gaurav, we can see your slide. Only thing is, it is yeah, now it is in presentation mode. Gaurav, are you speaking? Gaurav, we can't hear you. Gaurav, you're not audible. Are you speaking or?
It seems Gaurav has not enabled his audio. He has to click on connect with audio.
Oh, okay. Okay. I will call him maybe on the phone
Sure.
and let him. I'll call. Gaurav. So we can't hear you on this thing. So did you join with audio? Then maybe, or if you just refresh or maybe join again, then maybe, because your audio we are not able to hear.
Yeah, he is connected using audio.
Yeah. Hello, am I audible?
Yes,
Yes,
you're
you
audible.
are.
Yeah, thanks.
Yeah.
So Gaurav, I'll just briefly introduce you and then you can get started.
Sure.
Yeah, you can make full screen. Yeah, good afternoon and welcome you all for this second session of the tutorial on IoT. So I'm Raj Babu, and today's second session will be by Professor Gaurav. So the morning session, the first one of this tutorial was on introduction to IoT and sensors in IoT context. So this session we'll have Professor Gaurav talking about networking of IoT nodes. And then the last session, which will be the third session, which will start at 6:10 in the evening, will be on a lab session. So let me briefly introduce Professor Gaurav. Professor Gaurav is a faculty from our EE department. He did his PhD from UPenn, and he has been on our faculty since 2014 at least. So without and his area of research is in networking, wireless networks, and allied topics. And he has been doing also research in IoT and communication aspects of IoT. So Gaurav, may I please request you to now continue with the session. And there may be questions in between, Gaurav. If so, I will let them ask the question. And if it seems to get a little more prolonged, we can cut short that discussion. And since we are starting about 10 minutes late, we may still have to end it in time because because it seems there is a following session. So let us try to finish by 4:50.
Fine. Sure. Thanks a lot, Rajbabu, for the introduction. So this talk is on networking aspects of IoT node. As introduction, now the bullets are not appearing. Just a minute. Yeah. Internet of Things is an emerging and promising technology with a variety of applications, and different aspects of IoT are being extensively researched upon. IoT is extension of internet connectivity to resource-constrained devices such as sensors and actuators and everyday objects. It allows the remote monitoring and control of such devices. So henceforth, we refer to IoT nodes as henceforth we refer to such different devices such as sensors and actuators as IoT nodes. IoT nodes also communicate among themselves with minimal or no human intervention. This is called machine-to-machine communications. In this module, we study how IoT nodes can efficiently communicate among themselves and with traditional internet-connected devices, for example, desktop and laptop computers and smartphones. As motivation, some applications of IoT are as follows. One is precision agriculture. In this application, sensors are deployed at various points in a farm. So this is, suppose this is a farm and this is a wireless sensor network. And they monitor different quantities such as soil moisture, composition, temperature, humidity, etc. These measurements from the sensors can be monitored remotely, and they are used to control irrigation, fertilizing, etc. Then another application is smart healthcare. In this application, the sensor devices are attached to the patient's body. They collect medical data and vital signs. For example, blood pressure, body temperature, cholesterol level, heart rate, etc. from the patient. This enables the automatic diagnosis of conditions and tracking of progress. Anomalies can be indicated directly to the healthcare provider without significant human involvement. Another application is smart home. Here, an automatic lighting system senses the presence of human beings and switches on the lights only in specific areas of the house accordingly. Then another application is the automatic control of heating and air conditioning, for example, to avoid heating or cooling an empty home. Smart appliances can be remotely switched on or off over the internet. Then another is security. For example, motion sensors to sense intrusion by burglars, transmission of alerts to the homeowner's smartphone. Another example within smart home is home automation for the elderly and disabled, making it easier for the elderly and disabled to remain at home safely and comfortably instead of being moved to a healthcare facility. Another application is infrastructure machine monitoring and preventive maintenance. In this application, sensors are fixed to machines in a factory and walls of buildings, bridges, etc., which sense vibration patterns, acoustics, etc. They send alerts when maintenance is needed. Then another application is smart cities. Another application is intelligent transportation system, where an example is when different vehicles are fitted with GPS sensors, which provide their location, and the location is sent via, for example, a cellular network, say 4G, to a base station, and from there to the transportation manager's smartphone. Then another application is industrial automation. So we provide some background on communication networks. Recall that the basic networking functions are routing, reliable data transfer, congestion control, and medium access control. We focus on the medium access control function for the purpose of this talk. In the medium access control problem, n nodes are connected to a broadcast medium. If exactly one node transmits at a time, then the packet is successfully received. There is a collision if transmissions of two or more nodes overlap. None of the packets can be decoded due to interference. We need a way to make sure that exactly one node transmits at a time. So, for example, this is a successful node transmission, and this is another successful node transmission, whereas this is a collision because nodes 2 and 3, the transmissions of nodes 2 and 3 simultaneously overlap partially, and this is another instance of a collision. Medium access control protocol, it's a distributed algorithm that determines how nodes share the channel. That is, it determines when a given node can transmit. The MAC protocol should attempt to maximize successful transmissions like these, and minimize collisions, and minimize idle time intervals such as these. The types of MAC protocols are channel partitioning and random access. The channel partitioning protocols, in channel partitioning protocols, the channel is divided statically into smaller pieces, so for example, time slots or frequency bands. For example, this is a frequency axis, and this frequency band is divided into different subbands, and this is the time axis, and each piece is allocated to a node for exclusive use. And this is the time division multiple axis, where time is divided into frames, and each frame consists of multiple slots, and node 1 transmits in each slot. Node 1 transmits in the first. Node 1 transmits in the first. Node 1 transmits first in every frame, and node 2 then transmit. Node 2 does not transmit in this example, and node 3 then transmits, etc. Then another instance is random access based MAC protocol. The channel is not divided into pieces and collisions may occur. Each node with a packet to transmit waits for a random duration before transmitting to avoid collisions. The basic principle of random access protocols is as follows. Suppose packets are generated at nodes 1 and 2 at roughly the same time. If they transmit immediately, then a collision happens. If they retransmit, repeated collisions happen. So your packets are generated at nodes 1 and 2 almost simultaneously. And if they transmit simultaneously, then a collision happens. So if they try to compensate for the collision by retransmitting, then another collision happens. So a way to avoid collisions is that each node waits for a random amount of time before it transmits. Next, we discuss licensed and unlicensed bands. Some wireless transceivers, for example, Wi-Fi and Bluetooth, operate in industrial, scientific, and medical bands. There is one band around 2.4 gigahertz, and there is one band around 5 gigahertz, and there is also one band around 60 gigahertz. These are originally meant for purposes other than telecom, for example, microwave ovens. Later, unlicensed use by wireless devices such as Wi-Fi or Bluetooth was allowed. They must tolerate the interference from microwave ovens, etc., and other networks operating close by. On the other hand, cellular networks, for example, 1G, 2G, 3G, 4G, and 5G, they operate in the license bands. Typically, cellular operators acquire licenses by participating in spectrum auctions. Cellular networks do not suffer from interference from other networks. So, since say a company like Airtel participates in an auction and acquires some spectrum, so another operator, say V, or say Reliance Jio, cannot transmit on the same spectrum. So because the spectrum has been purchased by Airtel, hence it is possible to provide quality of service guarantees such as delay guarantees. Next, recall that the layers in the internet are the application layer, transport layer, network layer, link layer, and the physical layer. Where the application layer is where applications such as email and file transfer reside. The transport layer is where TCP and UDP protocols reside. Network layer it takes care of addressing and routing. And the link layer sends a packet across from one node to an adjacent node. And the physical layer sends bits on individual links as opposed to packets. So, for example, putting together bits into putting together a stream of bits into packets, and putting together a stream of bits into packets, and adding a checksum and sending it. That is done by the link layer, whereas the physical layer is sends the individual bits on the link. Now, what are the challenges in the networking of IoT nodes? Existing internet protocols such as TCP and UDP were not designed for IoT nodes. IoT nodes, for example, sensors and actuators are typically designed for low cost and low power consumption. So IoT nodes have limited available power. They are often battery operated, and they have limited memory. They also have limited processing resources. For example, they may have a microcontroller as opposed to, for example, they may have a microcontroller as opposed to, say, a powerful processor. They are disabled for long time intervals called sleep periods to save energy. Now, IoT nodes have different data traffic characteristics and quality of service requirements from those of traditional devices connected to the internet. For example, network access often needs to be provided to an extremely large number of IoT devices. For example, several sensors in each smart home. IoT nodes may transmit small bursts of data periodically or randomly. For example, soil moisture, temperature sensors in precision agriculture, etc. They may have stringent latency requirements or need priority access to communicate alarms. For example, in healthcare and security applications. They may require highly reliable communication, for example, in remote payment systems. They may require high throughput, for example, in a video surveillance application. Here an example is CCTV. Here an example is CCTV. IoT node access methods. Access network connects IoT nodes to the infrastructures, for example, the internet. The access network can be either wired, for example, cable, DSL, optical, or wireless. Let's discuss each of wired and wireless in turn. So wired access, the advantages are they can provide high reliability, high data rates, small delay, etc. So for you can connect a cable directly. The disadvantages are they are expensive and difficult to scale, and they cannot support mobile IoT nodes. Then wireless access, they are over short range, for example, Wi-Fi, and IEEE 802.15.4. So IEEE 802.15.4 is related to ZigBee, but there are some differences which we'll discuss later. And an example of wireless access is wide area or cellular networks, for example, LTE Advanced and 5G. And another example of wireless access is low power wide area networks. An example is LoRa and Sigfox. Short range wireless, for example, Wi-Fi and IEEE 802.15.4. Their advantages are that they are inexpensive. We do not need to connect a cable. Then they are scalable, and they are low power. And the disadvantages are their data rates are low, and they have yeah, I mean, there is the problem of lack of universal coverage, and they suffer from interference. For example, Wi-Fi microwave ovens share the same band with the with Wi-Fi with Wi-Fi transmissions, so that they may suffer from interference. And wide area cellular networks, for example, 4G and 5G. The advantages are that they provide ubiquitous coverage and mobility, and no interference from other networks. For example, if Airtel purchases a band by participating in a spectrum auction, then it is guaranteed that no other provider, it is illegal for other operators to transmit on the same spectrum. Then the disadvantages of cellular networks are due to a high demand for human-to-human communication services, for example, voice and data. Only a limited amount of radio spectrum is available with cellular operators to support IoT node communication. Fine. So next, now we discuss 802.15.4 in some more detail. Note that ZigBee and IEEE 802.15.4, they are related, but there is a difference that 802.15.4 is an IEEE standard, but ZigBee is a specification based on the IEEE 802.15.4 specification. So for details, you can refer to the Wikipedia page for ZigBee, as well as the Wikipedia page for 802.15.4. I mean, for a start. Fine. So now, having briefly mentioned the difference between ZigBee and 802.15.4, we now discuss 802.15.4 in some more detail. It's a standard for low data rate, low power, and short range radio communication. The IEEE 802.15.4 standard is maintained by the IEEE 802.15 working group. The complexity of the standard and the cost of related, the complexity of the standard and the cost of necessary hardware is low. It makes it suitable for wireless communication among constrained devices such as sensors and actuators. The 802.15.4 standard defines a physical layer and a medium access control layer. Medium access control sub-layer. So recall that the link layer. Recall that the medium access control layer is a sub-layer of the link layer. So 802.15.4 standard defines a physical layer and a medium access control layer. It does not define the higher layers, that is routing, transport layer, and the application layer. So first we briefly discuss the 802.15.4 physical layer. It is responsible for activating radio transceiver or deactivating it, for example, to save energy. It is also responsible for data transmission and reception, and for channel frequency selection. The energy detection within a channel and determining whether or not it is occupied. For example, clear channel assessment. IEEE 802.15.4 defines a total of 15 different PHY modes. The PHY mode defines the PHY mode specifies which frequency band and modulation scheme are used for data transmission. The 802.15.4 compliant radio typically operates in one of the following unlicensed frequency bands. 868 to in Europe, the 868 to 868.6 megahertz, and in North America, 902 to 928 megahertz, and the ISM band worldwide is between 2400 to 2483.5 megahertz. So these are the reserved. Sorry, these are the unlicensed bands used by 802.15.4. Now recall that binary phase shift keying and quadrature phase shift keying, etc. These are constellations for modulating the signal. So in the 802.15.4 physical layer, offset QPSK and binary phase shift keying are the most commonly used constellations for modulating the signal. Also, almost all of the defined 5 modes apply a spreading technique. It allows spreading out the signal so that it occupies a larger bandwidth. This makes the communication more robust. This has an increased resistance to interference and noise, even when using a low transmission power. Now, depending on the environment and 5-mode use, the communication range varies between 10 meters and 100 meters. Now, the maximum file data rate for the ISM band is limited to 250 kbps when using direct sequence spread spectrum DSSS, and 1000 kbps when using chop spread spectrum or CSS as the spreading technique. However, CSS is an optional feature of the standard, and in most applications, 250 kbps is the maximum file data rate. Fine. So now we discuss the 802.15.4 MAC sublayer. When a device wants to send a packet, the MAC sublayer asks the physical layer's clear channel assessment function to check whether the medium is occupied. If the clear channel assessment function indicates that another transmission is currently taking place, then the MAC sublayer defers its transmission to a later point in time and waits for a set amount of time before it retries sending the packet. However, if the clear channel assessment function determines the medium to be free, then the MAC sublayer transmits the packet immediately. The CSMA-CA protocol is used for contention resolution. This stands for carrier sense multiple access collision avoidance. The MAC sublayer also provides acknowledgement of packet reception. Fine. So next we discuss the validation of incoming packets using the frame check sequence in the MAC header. It is a type of checksum, this frame check sequence. Now, to limit the energy consumption, duty cycles are often used by medium access control protocols. As a result, transceivers can be in sleeping mode for up to 99% of the time, which this is useful for reducing the power consumption and increasing the operational lifetime. So as we have already seen, because of the since many of them are battery operated, it is useful to be in sleeping mode. In this 802.15.4, they can be in sleeping mode for 99% of the time and thereby conserve energy. Now, the maximum size of an 802.15.4 packet is 127 bytes. So, for example, we discussed the agricultural application where short packets of, say, soil moisture, some sensor readings need to be sent. So this 127 bytes is enough for sending such chunks of data. Now note that typically data packets are generated by IoT nodes. They are small in size, as we discussed in the soil moisture and soil moisture case and soil moisture, temperature, humidity, etc. Next, we discuss the LTE advanced architecture for IoT nodes. The LTE advanced architecture comprises of two parts: the core network and the radio access network. Fine. So this figure shows this is the core network. So we are talking about LTE advanced here. So this is the core network, and this is the radio access network, where the base stations are transmitting, where the base stations are exchanging information with the with different devices. The radio access network is responsible for wireless communication, and it consists of base stations, all referred to as these base stations are referred to as eNode Bs in LTE advanced architecture. They are connected to the core network and to each other. Next, the IoT nodes or also called as machine type IoT nodes or machine type communication devices connected to the eNode Bs. They connect by direct wireless link or via the MTC gate, MTCG or MTC gateway. Yeah, so here is an instance of the MTCG. The MTC, here a camera sensor, a health sensor, and a smart building automation. Here the camera sensor sends some information to the MTCG, and here some e-health sensor sends some information to the MTCG. Now, MTC devices can also communicate among themselves directly. For example, we can see, these two devices communicate among themselves directly. Next, the MTC to eNode B and MTCG to eNode B links are LTE advanced links. Now the MTCG to MTC and MTC to MTC links can be based on LTE advanced or short range wireless technologies, for example, Wi-Fi 802.15.4. Fine. So next we discuss random access.
Gaurav, I have a question.
Yes.
In the previous slide.
Yeah.
So all this, even this inter-device connections are also through LTE, or is it an option? It's optional, or is it only the communication to this tower-like thing, which is LTE?
This communication can be either directly, for example, between this smart grid related sensor and vehicle tracking, or it can be from this MTC device to the eNode B. Or it can be from this MTC device to the MTC gateway, and from the MTC gateway to the eNode B, and thereby from there to the core network. So in each case, all three possibilities are all three possibilities are there.
Okay. Yeah. Thanks. Continue.
Fine. So next we discuss the random access procedure. This shows the random access procedure. First, there is a random access preamble sent, and a random access response is sent, and then there is a scheduled transmission, and then contingent resolution. Then the minimum resource unit is called a resource block. 180 kilohertz in the frequency domain and 1 millisecond in time domain. When a UE, for example, a mobile phone or IoT node has packets to transmit, it performs random access on a time frequency resource called PRAC or physical random access network. Physical random access channel. That is, it sends a randomly selected preamble code sequence to the eNode B. Different preambles are orthogonal. So if two or more UEs simultaneously transmit different preambles, then a collision will not occur. But if multiple UEs transmit the same preamble simultaneously, then a collision occurs. If an eNode B receives a preamble, it sends a random access response. Subsequently, the UE sends the data packet it wants to transmit. Fine. So next we discuss PRAC overload control. Typically, the amount of data transmitted by IoT nodes is small, as we saw in the agriculture and smart healthcare and smart home, etc. applications. However, the number of IoT nodes in a cell is expected to be very large. Also, their frequency of sending data packets is much higher than in the case of H2H communication. Now, when a large number of IoT nodes try to access the network simultaneously, it leads to network congestion and low data transmission success rates due to collisions. It leads to a wastage of radio resources and packet delays, and also a wastage of energy. So because of collisions, this happens. And PRAC can be further overloaded when the IoT nodes repeat their access attempts after collisions. So because of this, efficient overload control mechanisms are required. Now, several mechanisms for PRAC overload control have been proposed, and we'll discuss them. One is the access class bearing or ACB scheme. And eNode B broadcasts an access probability and access class bearing time. When a device wants to initiate random access, it draws a random number between 0 and 1. If the number is less than AP, then the device is allowed to proceed with the random access process. Otherwise, the device delays for the access class bearing duration. Next, different access classes, each with a different access probability and access class bearing time are defined. Fine. So next we discuss the slotted access scheme. The time frequency resources are divided into different access slots. Each IoT node is assigned a dedicated access slot. Multiple IoT nodes may be assigned the same access slot, and in this case, via the random access, via some protocol like say slotted Aloha or CSMA-CA, the contention is resolved. Each IoT node is allowed to perform random access only in its assigned access slot. Next, we discussed the dynamic allocation of RA resources. Fine. So the PRAC load and data traffic load estimated. Out of all the time frequency resources available in a frame, the amount that is to be used as PRAC dynamically selected based on estimated PRAC and data traffic load by solving an appropriate optimization problem. Fine. So next we discuss the clustering of IoT nodes. IoT nodes can be grouped into different clusters based on their geographical locations. Each cluster is assigned one IoT node as cluster head, and each IoT node of a cluster communicates with its cluster head and not directly with the eNode B. The cluster head relays traffic between cluster members and eNode B. And the volume of random access requests from IoT nodes to the eNode B is reduced. Next, we discuss the pull-based scheme, where the base station initiates the transmission of data from the sensors or actuators to the core network. An IoT server that requires data, for example, sensor readings from IoT nodes, requests the eNode B to page the IoT nodes. Upon receiving a paging request from the eNode B, an IoT node starts the random access process. Thus, the eNode B can control the number of nodes to be paged based on the PRAC load and resource availability. So the disadvantage. What is the disadvantage of this scheme? So the extra control channel resources are required to page IoT nodes. Fine. Next, we discuss low power wide area networks, abbreviated to low power wide area LPWAN. So they provide long range coverage. The range varies from a few kilometers in urban areas to over 10 kilometers in rural areas. They can also enable data communication in indoor and underground locations. If there's a line of sight from the transmitter to the receiver, then the range is longer than if there is no obstruction between the transmission and receiver. So the range is longer when there is for example, in free space, as opposed to in the case of underground communication. And they also consume a small amount of power. They run on small inexpensive batteries for up to 20 years. They have low cost. And simple lightweight protocols are used, which reduce the complexity in hardware design and lower device costs. They do not require the use of any infrastructure such as Wi-Fi or cellular networks. For example, the reason is that a LoRa node can directly send information to the LoRa gateway. Now they are currently being deployed for various IoT applications, including smart cities and building management systems, and for precision agriculture. Some popular LPWAN technologies are LoRa, Sigfox, Ingenu, RPMA -7, and weightless. So we will discuss LoRa and Sigfox in detail. So LoRa is a proprietary technology.
Gaurav, just to
yes.
this is Raj Babu, just
Yes.
reminder. So we have about 20 minutes. So maybe if we can find a plan for 15 minutes, maybe we can have some questions at the end. That's okay.
Sure. Okay, fine. So it uses a medium access control layer protocol based on Aloha. Now the long communication ranges 15 kilometer plus are achievable in urban environments with no clear line of sight using LoRa nodes. It uses the 868 megahertz band in Europe and 915 megahertz band in North America and 865 to 867 megahertz band in India. these unlicensed bands are used for communication. And the maximum data rate of 50 kbps is achievable. It's sufficient for most IoT applications. Fine. So LoRa network architecture is a star network topology. And each IoT node or end device has a direct single hop connection to a LoRa gateway. The LoRa architecture consists of end devices which are shown here, and the server and gateways and remote terminals as shown in the figure. It uses proprietary chirps spread spectrum modulation scheme. And also another form of spread spectrum is used, frequency hopping spread spectrum. To mitigate the effect of interference, LoRa uses frequency hopping spread spectrum. Next, we talk about LoRa bandwidth. Bandwidth is the width of frequencies in the transmission band. Higher bandwidth gives a higher data rate, thus shorter time on air, but a lower sensitivity because of integration of additional noise. A lower bandwidth gives a higher sensitivity, but a lower data rate. I think, yeah, fine. A lower bandwidth gives a higher sensitivity, but a lower data rate. And a lower bandwidth also requires more accurate crystals, less parts per million ppm. Data is sent out at a chip rate equal to the bandwidth, and a bandwidth of 15 kilohertz corresponds to a chip rate of 125 kilochips per second. Yeah, so yeah, sorry, there is some repetition here. So I'll go through this slide first and then elaborate on spreading factors. So the LoRa transmission parameter selection problem is to ensure efficient and reliable communication. The LPWAN devices often provide a large number of transmission parameters. A LoRa device can be configured to use different spreading factors, bandwidth settings, coding rates, and transmission powers, resulting in over 6720 possible settings. So we'll discuss the spreading factor in detail, and the others, bandwidth settings, coding rates, and transmission powers we'll ignore. We'll omit from this talk. It is a challenge to determine the setting that minimizes the transmission energy costs while meeting the required communication performance. Fine. So spreading factor is the ratio between the symbol rate, data bit rate, and the chip rate. A higher spreading factor increases the signal to noise ratio and thus the sensitivity and range, but also increases the airtime of the channel of the packet. The number of chips per symbol is calculated as 2 to the power SF. For example, with an SF of 12, 4096 chips per symbol are used. Now each increase in the spreading factor halves the transmission rate and hence doubles the transmission duration and ultimately the energy consumption. The spreading factor can be selected from 6 to 12 in LoRa. As we have shown in, as has been shown in previous work, radio communications with different spreading factor are orthogonal to each other, and the network separation using different spreading factors is possible. So the reference, this reference is the relevant reference is this Bohr and Roddick. Fine. So next we move on to Sigfox. It's a proprietary technology and it provides a complete end-to-end connectivity solution. It uses ultra narrowband. The band of 100 hertz bandwidth is used. Since IoT devices require a small amount of data to be transferred, Sigfox suits such applications. It uses the 868 megahertz band in Europe and 915 in North America and 865 to 867 in India, unlicensed bands for communication. Fine. So now the end devices transmit on the uplink using differential binary phase shift keying, dB/PSK modulation. Base stations transmit on the downlink using Gaussian frequency shift keying modulation, and the typical transmission range in rural areas is 30 to 50 kilometers because of the relative lack of obstructions, and in urban areas is between 3 and 10 kilometers. Now the packet size of each message can be at most 12 bytes. Fine. Now the Sigfox network architecture is shown in this figure. There are some end devices which need to send some information to the cell tower, and then the cell tower. I mean these devices need to send to the. This is another server. Fine. So now we discuss node cardinality estimation. So the node cardinality estimation problem is as follows. Consider a network in which there is a single base station and a large number of IoT nodes in its range. For example, so the context here is that there is a base station, and around it there are a lot of devices. IoT nodes use a randomized MAC protocol for transmitting their data. For example, sensor measurements to the base station. Time is divided into frames of equal durations. Now, in each frame, only a subset of the IoT nodes are active. That is, they have data to send to the base station. Now, the key component of a MAC protocol for such a network is an estimation protocol that rapidly estimates the number of active devices in each time frame. These estimates can be used to find optimal values of various parameters of the MAC protocol. For example, contention probability, contention period, data transmission period, etc. in each time frame. For example, recall that for the slotted Aloha protocol, the optimal contention probability is the reciprocal of the number of active nodes. Fine. So now we discuss the lottery frame-based protocol. It is designed for finding an estimate, say n hat of the number of active nodes, say n, to within given accuracy requirements epsilon and delta. The user requires that P of mod n hat minus n is less than equal to epsilon n for greater than equal to 1 minus delta. The LOF-based protocol consists of m independent trials, each consisting of t time slots, where n-all is the total number of nodes manufactured and t equals log to the base 2 of n-all. Now, m is a function of the accuracy requirements epsilon and delta. This figure shows us a single trial of the protocol. After the trial, each slot of the trial can be in one of the following three states, either empty or success or collision. Let j of m be the smallest number such that the jth slot is in the empty state in the m trial. At the end of all m trials, the estimate of n is computed as n equals 1.2897 into 2 to the power summation m equals 1 to m hat small m equals 1 to capital M, jm minus 1 by m. Fine. So next we discuss the simple RFID counting protocol. So it's a two-phase protocol. At the end of phase 1, it finds a rough estimate n tilde, and at the end of phase 2, it finds a final estimate n hat. Phase 1 consists of a sequence of multiple trials of the LOF-based protocols, LOF-based protocol, and phase 2 consists of a single trial of L slots, where L is a function of epsilon. Each active node independently practices, each active node independently participates in the trial with probability P and does not participate with probability 1 minus P, where P is the minimum of 1, 1.6 L divided by n tilde. Also, each node that participates transmits in a slot selected uniformly at random from the L slots. Fine. So the protocol counts the number of empty slots, say Z, out of the slots of phase 2. The final estimate generated by the protocol is n hat equals ln Z by L divided by ln 1 minus P by L. Fine. So next we discuss the multiple set simple RFID counting or SRCM protocol. First, what are the applications? What is the motivation, or why do we study this? So the applications are from our prior work. So mobile base stations, such as those mounted on unmanned aerial vehicles, are robust, highly mobile and agile, and have wide coverage capability and high battery backup capacity, and are being extensively deployed in various military and civilian applications. MBSs can be used for estimating the number of active nodes, such as moving vehicles and traffic control systems, agricultural field monitoring sensors, people affected in disasters such as floods, wildfires, etc. MBSs are used to estimate the number of vehicles moving on some congested roads per hour, so that an efficient traffic controller can be designed. So this illustrates the context. So there is a vehicle which is a vehicle here, which moves to this location, then from this location to this location, from this location to this, and so on. So and there are different types of nodes which are shown by different symbols in this figure. The integration of constrained devices into the internet. Next, we discuss the integration of constrained devices, for example, sensors and actuators into the internet. Recall that internet technology is rapidly spreading to new domains where constrained devices such as sensors and actuators play a prominent role. This expansion of the internet is comparable to the spread of the internet in the 90s. The resulting internet is now called the Internet of Things. The integration of constrained devices into the internet introduces new challenges, since most existing internet protocols were not designed for constrained devices. Constrained devices, for example, sensors and actuators, they are typically designed for low cost and low power consumption. They have limited power and memory and processing resources, as we have seen earlier. And they are often disabled for long intervals or sleep periods to save energy. Now, initially, several proprietary protocols and architectures were developed by different companies to enable the integration of constrained devices into the internet. So later, the integration of constrained devices into the internet was taken up by the Internet Engineering Task Force. They moved towards standardized IP-based protocols. So IETF, the Internet Engineering Task Force, started several working groups for this standardization, including IPv6 over low power WPAN or 6LoWPAN. It addresses the transmission of IPv6 packets over IEEE 802.15.4 networks, which we discussed earlier, and routing over low power and lossy networks, or a role. And it develops IPv6 routing solutions for low power and lossy networks, constrained RESTful environments, or core. It addresses the need for a counterpart of World Wide Web in constrained environments. It seeks to allow the integration of constrained devices with the internet at the service level. Fine. So next we discuss 6LoWPAN in some more detail. So we are all familiar with IPv4. So the IPv6 header is shown here. there is a version, these are all quite self-explanatory: version, traffic class, flow label, payload length, next header, hop limit, source address, and destination address. An IPv6 address is 128 bits in length, and IPv6 headers have one fixed header and 0 or more optional extension headers. Now, IPv6 fixed header is 40 bytes long and contains the following information. The version of Internet Protocol, that is 0110. The traffic class and flow label are not relevant to our discussion. The payload length tells routers how much information a packet contains in its payload. The next header is used to indicate the type of extension header when optional headers are present, or if extension headers are not present, then it indicates the upper layer protocol. The source address and destination address are the addresses of the originator and intended recipient of packet respectively. The hop limit puts an upper limit on the maximum number of links between two IPv6 nodes. 6LoWPAN, IPv6 protocol has. Yeah.
So we are almost close. So you can just plan, like we have 5 minutes, so maybe you can plan accordingly and probably start. Yeah.
Fine. Sure. Okay. So IPv6 protocol has high overhead, which makes it unsuitable for low power and lossy networks such as 802.15.4. For example, maximum size of payload of an 802.15.4 packet is 127 bytes. So use of a 40 byte IPv6 header would be excessive. Hence, the IETF 6LoWPAN working group was formed. Its objective is to work on the IPv6 protocol extensions required for networks where nodes are interconnected using 802.15.4 radios. The key protocols are as follows: IPv6 forwarding protocol. IPv6 forwarding routers do not support fragmenting outgoing packets. So I'll skip all this. So you can search for 6LoWPAN. Fine. So I discussed header compression. 6LoWPAN provides stateless compression. All the information required to compress and decompress a packet is contained in the packet. The sender receiver do not need to store any information. Some techniques used to compress the header are as follows. The version field is always 0110, so it can be omitted. And so I'll skip all this in the interest of time. The fragmentation, I'll skip. Fine. So routing protocol for low power and lossy networks, or RPL. Yeah, this illustrates the basic idea. So there is a source which needs to transmit to a destination. And why is it not directly sent? It is instead sent directly up to the route, and from the route down to the destination for simplicity. And here also, here it has a common parent early on in the up the hierarchy. So it sends it up the to this common parent and then down for simplicity. Now, point-to-point traffic can be routed in the non-storing mode, where the packet travels all the way up to a DODAG route before traveling down, and the storing mode, where the packet may be directed down by a common ancestor of the source and destination. Fine. So next we discuss the Constrained Application Protocol, or COAP. An IETF working group called Constrained Restful Environments was formed for allowing realization of embedded web services similar to the traditional web devices, but suitable for constrained nodes. Yeah, so anyway, so COAP is they designed this COAP protocol. So you can search for the details online, and the datagram transport layer security, or DTLS, provides secure communication. Fine. So resource discovery, the message can be used to request a list of resources hosted by a server, and fine. The observation, there is an observation function provided. Yeah, fine. So I'll just discuss this observation function. This is the last slide. The state of a co-op resource can change over time, and temperature is sensed by a sensor and observe option. Whenever there's a change in the resource state, the sensor sends a notification to the client, and thus the observe option offers the possibility for a client to have an up-to-date representation of the resource without the client having to constantly poll for changes. Yeah, that's all from my side. So are there any questions?
Yeah, so I don't see any question in the chat window.
I have a question.
Yes.
Please go ahead.
Sir, I would like to understand, like while selecting one of these technology or IoT communication, how to select means what will be the parameters we need to choose and how to select the particular technology from so many available technologies.
Yeah. So one would be, for example, between LoRa and Sigfox. So one example would be, for example, the speed or the bandwidth at which the data is transmitted. Another consideration would be the energy consumption of the packet. Yeah, I mean, these are some examples of yeah, I mean, these are some examples of considerations and the distance over which the packet can be transferred. That's another example.
Okay, thank you, sir.
Okay.
Any other questions? Yeah. Okay, maybe.
Okay, fine. So
Thanks,
thank you, everyone.
Gaurav.
Thank you, Rajbabu.
Yeah, thanks, Gaurav, for the talk, and thanks all for staying back. Also, would like to say that there will be a third session, which will be a lab kind of hands-on session, walkthrough session. So please join us for the third session. Once again, thank you all, and I think we will end this tutorial now. So, Pratibha.